right. Okay, so we got the last part about the observer pattern lecture. Okay, it's quite a long lecture. Basically, we talk about without the observer, with the observer, and the event-driven design. So those are the three parts you have to study later when you study for the exam. But we can do something in the review session as well. Okay, so what we did last time was to show you how you can do event-driven design in Java. Okay, that part is optional. You don't have to worry too much. It's only for your personal curiosity if you want to do it in Java. So let me review very quickly about what you should know about the story so far, and then we'll get to the final part for Eiffel using agent. Okay. Before that, let me just remind you very quickly. Okay. So you have already received an email from me just about scheduling review session for during the exam period. Go to the survey, just tell me your available time. I'll choose some times to that works for the most people. Okay, and also the two makeup lectures on November 15th and 22nd. Oh, wow. Okay. Review session survey, please complete it as soon as you can. Okay, so I'll know your availability. And also the makeup lecture on 15th and 22nd, they are covering the exam. Okay, just make sure you catch up with the lecture if you didn't attend. All right, let me just review very quickly about the story so far about the observer pattern lecture. Okay, that's the architecture diagram you should know about. Okay, about the observer pattern. Let me just tell you the thing that we should really care for today. Okay, the drawback about the observer pattern over here is every time if there's any change on the subjects, okay, you can see there's a subject, there's an observer over here. We have to somehow let the subject explicitly call the notify command over here. And what does the notify do? If you try to remind yourself, it will simply just be a cross loop. So let me remind you very quickly. You'll simply say across the observer is, let's say observer. And then you got to say observer.updates. So you can see somehow the responsibility of updating individual observer relies on the subjects. Okay, that's the observer pattern. However, we say that though this kind of pattern might create some complication when you got multiple subjects and multiple observers. Okay, that's why we want to move on to event-driven design. Okay? That's something you want to pay attention to. But observer pattern is not bad. It's very commonly used. I would say if you don't have anything available for you to do elegant event-driven design, for example, in Java, you got to do method handle, which is quite complicated. I think observer pattern is still fine. Okay, but if you got event-driven design mechanism available, you should use it. It's ideal. Okay. Okay, I wouldn't say too much about observer. You should review it, and then that's kind of the limitation for observer pattern. You can see very complicated structure where you got actually multiple observer over here, and also you got multiple subjects and also multiple observers over here. Okay, you can see the complexity is actually quite huge. It's kind of quadratic on the number of observers and subjects. Okay, what we really want to do, okay, is move on to this particular much more simplified diagram over here. So we still got multiple subjects, we still got multiple observers on both ends. But now what you have to design is the number of events that's going to occur when changes happen, right? In our particular case for the weather station, we got temperature, and also we got pressure, and also we got humidity. Okay? So these are the three so-called monitor variables, right? If you look at the slides, there's also a term, monitor variables. So these are the variables that will be monitored by observers somehow. Okay? We want to make sure now the responsibility of calling the observer to updates should not be the responsibility for the subject anymore. It should be the events. Okay? Let me just mention again conceptually, and then we'll go to the code. The way to understand the event-driven design is two stages. Okay? One is about subscription. The other one is about publication. Okay? Let's talk about subscribe stage first. Every time if a particular observer, let's say the app, for example, forecast app. Oh, actually, you know what? Let me say current condition app. That'd be better. Let's say current condition. Okay, that's one of the apps that we talk about. Let's say for this particular current condition app, we are trying to create that at the runtime. It's going to subscribe itself to the events it cares. And one of the variables that current condition monitors is the temperature, right? We want to know what's the current temperature. So now when you try to subscribe, so this particular direction over here is really important to say, at this moment, we don't need to update the temperature just yet. No changes have just happened. We don't have to, okay? What we will do is, when we try to subscribe, we're going to attach a pointer to the updates function for temperature. So we only attach the reference. And what's the purpose of that? Once you get a reference stored somewhere in the events, when changes really happen later, we can execute that reference. Okay? It's like a pointer to function as you learned in 2031. Okay? Okay, so now the most important part to know about this is for delay execution. Once we see how this can be done in Eiffel, hopefully that'll be even clearer. Okay, but the main thing about the subscribe stage is about delay execution. Okay, that's the first stage. The second stage you should really pay attention to is when something that really happens. Let's say the weather data has been updated so that maybe the temperature goes higher or lower, right? There's an update. So now we're going to the publication stage over here. So that's publish. So now when the subjects actually publish whatever temperature, for example, the temperature goes higher by 1.5 degrees, for example, right? In that case, as soon as the events receive this particular publish notification, in that case, what they will do is they're going to refer to whatever pointer that's been attached to previously when all the observer, when they try to subscribe, right? What they will do is they will try to execute these pointer to function and then do the updates right away, okay? So now you can see this is, let me write it down. When there are updates from the subjects, the events will execute the pointers to functions stored previously. Okay, so these are the two stages, right, conceptually. And these two concepts are actually implemented in Java and Eiffel. But we want to see how different it might be. Oh, we already saw the Java one, which is quite sophisticated, quite many classes you got to pay attention to. But now, in the Eiffel case, it's a little bit cleaner. So we want to see exactly how to do it, okay? Okay, let's have a look quickly. Okay, I'll show you a little bit code on the slides, and then we'll see how things work together at the runtime, and then do a little bit comparison, and then we are done for this particular topic. Okay, so now the most critical class you should have is called events. Okay, this is not a class in the library you have to create it by yourself. Okay, event class, and this event class is somehow similar to the event class we talk about in Java. So they were chosen the same name for a purpose. Okay, so you can contrast. Okay, and then we talk about this arrow greater than, dash greater than is constraint genericity, which means whenever you instantiate this particular generic parameter over here, it must be a subclass of tuple, basically any tuple. Okay, and then we got to make for events, and now this is somehow similar to what you saw for Java. So now we're making that simpler. Line number 4, we simply say every event at the runtime is going to maintain a list of procedure. And the procedure over here you can think about as pointer to function for delay execution. Okay? So now let me show you quickly a diagram over here. So at the runtime, okay, you can think about at the runtime for every subject like weather data. They contain basically several events, maybe change on temperature, and change on pressure, and change on humidity, right? You got different events. Every event is going to have an actions. Action would just be a list of procedures, like a pointer to function. That's what you will see, okay? I haven't started tracing the code yet, but I will, okay? I just want you to visualize this is what's gonna happen at the runtime. We've got 3 separate events to be look over. Okay, let's go back here, and then we simply create the linked list of events to be procedure to be empty to begin with. So now how do we subscribe? Well, subscribe, given a pointer to function like a procedure, we'll simply make sure it has not been added so far. And then we add it using extend, and then make sure it is there. A very straightforward implementation. And what about publish? So now if you recall what should be done in the Java side, what we have to do is we got to retrieve from the hash table in the Java side, and then call that particular method that's been stored previously, right? Similar idea over here, but the syntax is a bit easier. What you got to do is you'll simply, let's say in this case, I just run a from loop. Basically go over every, okay, not too sure what it is, okay? Go over every action in the linked list, go over every one of them, and then simply try to invoke them together. Okay? You simply say actions.item, so this will be a pointer to function, and then you simply call with whatever argument you have. Okay? That's the event class. So if you actually try to compare this particular class with its counterpart in the Java, they are pretty much similar. The only difference is in line number 4, rather than having a hash table with math handle, but now you have just a linked list with procedure. Okay? Any questions so far? Okay? Just for the event class, right? Yes?
So the argument is the type tuple. What's in the tuple?
Good question. So first of all, you can see from line number 1, we're saying that the parameter we declare for the type is called arguments, right? Which means it can be instantiated by anything that's a subclass of tuple. So that means when you actually try to instantiate the event, I'll give you one example, okay, right away. So now, okay, over here. I think that's good. Let me make it larger. So this is the event class that we talk about over here. Okay, how do you declare that? Okay. So one way to do it is you can simply say E1, for example. And now if I say events, I am expected to actually pass something over here. It can be anything as long as it's a tuple, right? For example, I can simply say, I will simply give you a tuple over here. I'll make a little bit more space for myself. Okay, let's say up. So I can simply say, for example, tuple, that's the expression over here, right? And then I'll say, for example, real. So this is basically an instantiation where the tuple has only one element, and one element is simply real. I'll give you one more example. Okay? And it can also be 2 arguments. I can say E2 over here. I can say events. It's a different events. But now it could be that it will simply be, for example, here, I can say string followed by integer. That's also fine. So it can be as many arguments as you like, depending on how many are needed. Okay? Yeah, you will see actually that later on in the event for the temperature, humidity, and pressure. Okay? Do you need to memorize the code? No, you don't memorize it, but understand it. Okay? Because in the exam, I might just give you the event class for free, no problem. But you have to know somehow how to complete certain critical parts. Okay? Any questions? We okay? All right. All right, let's go back here, and then let's try this. Okay, that's exactly what's said, right? It's going to constrain the arguments to be a tuple. Okay. All right, let's look at the subject very quickly. The subjects over here, you're going to say make. Okay, again, we got all the 3 variables as before, so nothing need to be repeated. And then also, let's see how we can declare events. We simply say we have change on temperature, and then you can see over here, I simply tuple real, right? Okay. And also, I got event and then tuple real as well. Because you can think about every event that we talk about right now is only involve a particular quantity. Let's say some real number for temperature, some real number for humidity, so only one. So there's only one necessary. And remember once keyword that we talked about before? Okay, maybe review that, what once really mean when we talk about singleton, okay? That's also important. Okay, and then we can set the measurements, and also we can also, over here, when we say set the measurements, so that means it's not the time to change the quantity for humidity, for pressure, or for temperature. So now we have to publish to the events. If you think about the diagram over here, you can think about whenever we say set measurements for the subjects, we have to publish this is the time to publish to the events, all the relevant events. Okay. So now if you look at that, we simply say change on temperature, which is the events, and then we'll publish. And now notice that when we say publish here, you're going to give a tuple of the temperature over here. So that means this particular temperature will be passed to the publish. And then it will be used to call all the delay execution that's stored for the observers. Okay, we'll see exactly that in just a moment. And then also we got change on humidity. And you can see we're also passing a single tuple, but you can see what we're passing here, the pressure, P. Okay? And also we got change on, oh, sorry. That one, it is typo there. It should be H, and this one should be P. Okay, you're just gonna pass the right amount over there. I'll fix that typo there. Okay, that's about the weather data side. We haven't seen the observer side yet. Observer side was very complicated in the Java version because you somehow gotta use a method handle to look up the table. But now, let's see if we need to do that. But before we see that, any question about the subjects here? We okay? Okay, any immediate question for me for clarity? Clarification. Okay, so that's about subject here. Basically, subject simply publish when they have the updated quantities. Okay, let's look at the one of the apps, the observer. Let's see how the observer is incredibly simple. Okay, there's no lookup like a method handle in Java. Okay, what we do is, again, we got a constructor over here, and oh, let me remind you quickly. If you compare what you have to do for event-driven design versus observer, back to the observer version, what do we have to do when we create a new app? Somehow there was a bidirectional link we have to build, remember? Last Friday when we talked about you have to somehow attach WD to the current app and also attach the current app to the subject itself. There's no such bidirectional link for the event-driven design. Okay, something to note. What I meant was, okay, in case you're a little bit lost, you better review this particular part, okay? What I'm saying is, in the case of the observer pattern, okay, that's kind of the complication comes from. In the case of the observer, you want to make sure application is attached to the weather data. And also weather data is also attached to the application, right? So there's a bidirectional link. And then in the event-driven design, there is no direct link between the subjects and the observer. There's no. All you do is the subject is only linked to the relevant events, whereas the observer is only linked to the relevant event as well. Okay, so the way you link things together is different. Questions?
Is that the unique characteristic of the observer pattern? Or, for example,
You mean bidirectional link?
yes.
When you say unique, I'm pretty sure such bidirectional links also exist in other design patterns. I'm just saying when you compare event-driven design versus observer design, that's how you can think of it. In the case of the observer, you got bidirectional link, direct links. But in the case of event-driven design, you don't have that direct links. Okay. All right, let's go back to the code quickly and let's see. Oh, so what this will do, so now in the case of the current conditions, because we know it really matters about the temperature and humidity. So that means we gotta subscribe this particular current condition. What do we subscribe? We subscribe whatever the update operation it would be necessary to be stored for delay execution. So now you can see we're using the word agent. Okay. As far as this course is concerned, how do you understand the agents? You can think about, let's consider these two syntax. Okay, both are valid. Okay, let me make it clear to you. Okay, I'll switch to iPad in just one moment. Let me copy that down. Okay. Update temperature versus another one. Okay, over here. I want you to really understand what's the difference between these two syntax. Both are valid syntax. Both are. But what would be the difference? First of all, if you look at the update temperature, okay, I'll show you the definition of that. If you look at that, update temperature is basically here. Okay, in the current condition class, we got update temperature over here, which will take some arguments. right? Which means we want to update the current temperature to be T, the arguments. So what's the return type of update temperature in this case? Does it return anything? No, it's like a command or like a void in Java sense, right? So now if you think about it, if you go back here, if you think about update temperature, what that really means is, number one, doesn't return anything. It's a command. Does not return anything. Because it's a command. And number two, which is more important, when we say update, when we call update temperature, is something going to happen right away, or it's going to be waited? Right away, right? So that's immediate execution. Okay, so that means to execute the implementation of update temperature right away. So that's pretty much what you would do in Java, always when you call a method. What about number two? For number two, even though you're still using update temperature, that simply says, I don't want to call update temperature right away. Instead, I'm going to retrieve its reference. Okay? So now to be more precise, with this particular agent keyword, so now the whole thing over here, the whole expression over here is of type procedure. And let me remind you, the procedure is exactly the type that's being expected, excuse me, expected by event class actions, right? You can see it's a linked list of procedure. Okay, that's how the types work together. Okay. So now, when you say agent update temperature, that means rather than executing the body of implementation for update temperature right away, I want to store its reference somewhere so that it may be executed when necessary later. Okay, that's the delay execution. Okay. Okay, for delay execution. Okay, any questions about delay execution here? Okay, yes. Is it the Eiffel defined class? Yes. So you can think about procedure as like a pointer to function type, as you learned in 2031. So rather than executing update temperature right away, I want to store its reference for later execution. Yeah. So that's the key, actually, for making event-driven design work. Okay? Okay, so now after this, let's look at what's next. Okay, so we are passing basically a reference to update temperature to this particular event, change on temperature. And we're passing another reference over here, agents, update humidity, and then we pass that to change on humidity, right, to the corresponding events. Which means later on, let's say this. Let me go back to this diagram over here. I can update that a little bit. You can think about when I try to do subscription over here, when I try to subscribe, what I'm passing over here is something like this. I'm passing the agents of updates temperature. Meaning that I'm not trying to execute this update right away. I'm trying to store its reference for delay execution. Okay, that's number one. And then later on, when there is any updates on, for example, weather data 1, in that case, when they try to publish over here, what they will do is they will simply go to whatever reference has been stored before and then execute it, right, in a different timing. Okay, that's how things work together. Okay, so now we got temperature, we got humidity, and then everything else is just the same. And that's it. You can see there's no mention about method handle, and also there's no lookup. There's no hash table, like what we said before. You can think, let me put it in a way that's simpler. In the case of Java implementation, you have to use a method handle. We somehow got some reflection mechanism that's sophisticated for Java. But now in the case of Eiffel, they got some built-in class called procedure and also a syntax called agent for you to do two things rather easily. In terms of computational complexity or in terms of computational efficiency, they're the same. It's pretty much the same amount of work that has to be done. But somehow many details were hidden in Eiffel side. Okay? Any questions so far about the class definition here before I try to trace a little bit code together with you? We okay? All right. Okay, let's have a look. So now what I would like to do is to, again, so this one simply tell you what agent really means. You can look at that. So now what I would like to do is I want to go over again the Testico over here. We're going to create some weather data, and then we're going to create some app, and then we'll see how things will work together in the case of the event-driven design. One thing to note, later on when you review the design pattern over here, you will see that the same fragment of code has been used for testing the different design that we talked about. The same fragment of code was testing the non-observer pattern, the first design. And the same fragment of code has been tested for observer design. And now we're using the same code again for the event-driven design. So that's how you compare the three different designs. Okay? So what I will do now is to go back to everything's here. I'm going to enlarge a particular part when necessary. We just want to see how things work together. But these are all the four classes you have to understand. Okay? We got, let's talk about the four classes very quickly. Okay? So over here we got weather station, we got current condition. Oh, so this is subjects, of course, weather station. And also we got, weather station is mainly the main control. Okay, that's where we write the test code. And then we're going to look at the observer current conditions, and also weather data is the subjects. And then somehow events will be used, okay, throughout the course of the core program. Okay, let's try to trace them a little bit to see how things work together. Okay, and eventually that's kind of the runtime diagram you will see. Okay, let's go one by one. Okay, now let me start with the first line of the execution when you run the program. And by the way, the program has been made available to you, so you're encouraged to try. Okay. So now let's do line number 1. We simply try to create a new weather data, okay, a new subjects. And then we simply say 9, 75, and 25. Okay, that one's easy. So 9, 75, and 25. That's all we do. And also, we initialize all the 3 events. They're simply like a normal attributes we have, right? Just normal, okay? So we got 1 event for the temperature, we got 1 event for the pressure, we got 1 event for the humidity, right? 3 events. At the moment, all their actions are simply just empty. You can think of that, just empty, okay? No events, no procedure has been subscribed just yet. Nothing has been there for delayed execution. Okay, let's go to the next slide. So now, if I go to the next line, this one will be important. So now, when I say creates current condition, the make, and then passing the weather data, the subjects, what's going to happen? So now, let's go to the make command for current condition. Okay, let's now switch the context over here. So now, let's go to the current condition here. So current condition here. So now, under the make over here, we have some weather data, WD. So what we would say is now we want to modify WD dot change on temperature, and also WD dot change on humidity. Again, it's a typo here. We want to modify these 2 relevant events. And how do we modify them? The way we modify them is defined by the subscribe command. Okay, have a quick look on the subscribe. If you now switch the context to events, right? So these 2 are of type events. Let's now switch to event right away. If you look at the event class over here, let me make it bigger. If you look at the events, so event is going to have the subscribe over here, which will simply extend its actions by whatever you pass to it, which is an action, which is a procedure. And how do we create a procedure? We use the agent keyword, right? So let's see that. Let's go back there to the current conditions. You can see over here, we're using agent. Would it be correct if we don't have the agents? It would not be correct, simply because if you simply got update temperature and update humidity right away, so that means I want to execute the body of implementation right away, which doesn't return anything, because these are commands. But if you use agent keyword, so that means I want to retrieve their pointers and store that in the events for delay execution. Okay? So now it's really important to see why agents should be there. Okay, so now let's have a look at over here, agents, update temperature, and also agents update humidity, right? So what that would do is, let's go back to the visualization here. So now update on temperature and humidity, okay? Update on temperature. So now the first one is going to store the agents updates on temperature. Okay, that's the feature we are storing, okay, the reference. Okay, and then we also try to do another change on humidity, right? Update on humidity. So update on humidity is going to be change on humidity, right? So now we're going to add another action over here, and it's going to be agents updates on humidity. Okay, this step is very critical. So what we have seen so far, you can see what we have seen so far, we're only storing the references of the update commands into the events. We don't really execute them just yet. You can think about these two references over here. These two references that store will be used to execute the commands to updates later when necessary. Okay, will be published from the subjects. Okay, so far we have seen over here just about the make feature over here, right? It's done. Finally, we want to look at what's going to happen when we try to say, I want to change on the weather data, so which means we want to publish something. Okay, that's the second stage we want to go through. Okay, let's see the final stage over here. So now we say wd.set measurements, right? So now let's go to the set measurements in the weather data class. Let's say 15, 60, and 30.4, okay? We just do some substitution there. So now we go to weather data over here, and we go to set measurements over here. And then let's copy the number 15, 60, 15, 60, and 30.4. Okay, that's what we are doing here. Okay, I'll just do one of them just to show you the idea. Okay, so what would I do for set measurements? Basically, number one, you have to update all the local variables for this particular subject. That's what you should do first. Okay, once you have done that, here's comes a very critical part. Remember previously, according to the diagram, we only store the reference, for example, for update on temperature. We haven't executed them yet, but now is the time. Okay, so now if you look at that over here, you can see change on temperature over here. For example, you're going to say publish. And then what you will do is you're going to pass a tuple. What's t? T is 15. That's what you're passing. Let's trace this one very carefully. If you go to publish, so now let's switch the context to publish for events. So now again, we're back to the event class and look at publish. If you look at publish over here, so now the argument is simply a tuple, and then let me remind myself, it's 15. So this is the value we are passing over here. Okay, we're passing a single value, which means this is the 15 is the value I want to update. And I want to update to all the delay execution, basically. So now let's have a look at the loop. We'll simply go over all the actions, and for actions, the item, so this will be a procedure. And then we're simply going to using 15 to execute. Okay? So at the moment, we only got one single procedure being stored over there. So how does that reflect over there? So that means in the very first iteration, we're going to see, okay, so this is the only reference we have. So now we are simply going to say updates on temperature. And then since it's only a single value, like a 15 over here, okay, so we'll simply call, 15 over here. And now this is now the time to execute the updates. You can see when you subscribe and when you publish, they don't have to be simultaneous. They're simply separate apart. So that's the beauty about event-driven design. So when the observers subscribe, they only subscribe the references to their updates. Okay. All right, guys, any questions?
Sorry, just a quick question. Is that we're actually storing the references and executing them at a later time?
Mm-hmm.
In the event class, when you want to check the references,
Yes.
call,
Mm-hmm.
like a feature that actually calls the references?
Exactly. Okay. So what Chelsea just mentioned was like this feature, this call over here. Okay. Again, we want to look at, you basically talk about this particular guy here, right? Call. Yes, call actually comes from the procedure clause. Yes. It simply means whatever pointer to function you get, now call that with this particular value. Okay. If you look at the Java version, you got something similar. Okay, but you don't have to worry about the Java details. Okay. Guys, any question in general about the event-driven design? It's not the time to ask for clarification. Or later is fine. Okay.
Is this a silly question? Is this during a runtime or is this during compile time? This picture when they store the reference. So is this reference?
Oh, runtime. So basically, when I was trying to trace a code for you, I kind of show you all the definition you should know about. And then when I try to trace it, I try to switch the diagram so often. So that's runtime for sure. So you can think about at runtime, maybe at different timings. First of all, we're going to store the reference at the runtime into one of the actions, right? The reference to, let's say, update on temperature. And then later, not simultaneous, later we're going to execute this particular store reference and I'll execute it to update the observer, right? Yeah, runtime, yes. All right? Yes?
So inside the array of actions, there's always only one procedure to call, right?
Oh, yes. Apparently, for this particular simple example, I only show you one procedure being stored in the array or linked list. In general, it can be maybe 10 or 15, depends. For example, let's say if you look at the diagram again, if you look at the general diagram over here, you can see we can have so many different observer, 1, 2, 3, 4, and so many, right? So that means the actions array over here, or linked list, can be arbitrarily long. It could be. So that's why we use a loop in the event class to actually go over them. Okay? Of course, it is possible, maybe, you simply got another one over here, and then you also got agents, and then updates on temperature. Okay, over here.
They can be polymorphic, right? They have to be.
Oh, good question. Good question. Okay, I would say don't bother with polymorphic. Oh, okay. I would say yes. It's going to be all procedure. In some ways, polymorphic because procedure is a subclass, descending class of itself. It's always going to be procedure.
The reason I asked that question, I was thinking of like using a stack.
You mean rather than linked list, you use a stack? Why would you use a stack? You know, in some way, the order of executing the updates on the observer doesn't really matter. So you don't really need the last in, first out order over here. So I would say either you execute, if you execute from left to right, I think that's fine, right? The main idea is really about to execute the delay execution you store. Right? All right, I think there's one more slide I want to go over, and then we are done with this topic, okay? So now the final slide, basically just to compare. Conceptually, Eiffel and Java, they are trying to achieve the same thing, conceptually. However, just a syntax that make it maybe one version will be harder, the other one will be easier, and that's the difference, okay? How do you store? In the case of Java, you're gonna get a hash table, get a current object, and also some method handle. It's an existing class in Java, right? In the case of Eiffel, you simply link list or procedure, okay? And now, how do you create and pass function pointers? In the case of Java, that's what you have to do, right? If you remind yourself what you saw last Friday, right? Basically, you have to call, look up, find virtual, and then give the context class, method name, and also return type, etc., and then put it into the hash table, okay? How would you do that in Eiffel? Well, a single line, okay? Again, conceptually, both are equivalent conceptually. However, it's really about when you implement it, one will be easier than the other. That's the difference, okay? All right, so after this, okay, so again, we're just saying for in terms of design, it's just easier to do it in Eiffel, okay? But of course, let's say later on, if you have to program in Java for your work, if you really want to implement event-driven design, you have to use method handle, unfortunately, okay? Okay, that's about the end of the lecture for observer, etc. Right? It's quite a long lecture. That's why we spend more than 2 classes. But any questions in general before I move on to a new topic? We okay? All right. Okay, so now let's move on to a new topic. And this might be the last topic for this course. Okay, but this will take some time. So this topic is about program correctness, okay? not too much about programming details. It's really about how we can justify that our design is correct. Basically, so far in the course, we really emphasize on having precondition, postcondition, and class invariants. So these are really something very useful for you to justify the correctness of your design, not just at the runtime. Basically, what you did in the lab so far, you simply have some runtime checks on your precondition, postcondition, class invariant. But you can also do it statically on the paper. Okay? Let's say you got some precondition, postcondition. Can you somehow justify whether your program is correct? That's something we'd like to achieve by the end of this lecture. Okay, we're gonna have at least two classes to talk about this. Okay, let's go gently in the beginning. Again, I'd like to just clarify some terminology here, and this somehow was addressed when we talk about subcontracting. Okay, again, we talk about assertion like a predicate, right? A Boolean expression. We talk about weak versus strong assertions. Okay, that's something we want to clarify first. Again, we can use example to talk about it. Okay. Okay. Over here, so now, one way to think about every assertion you have, like a precondition or postcondition class invariant, it's going to be a set of satisfying value, like a set. Okay. So now, for example, you got x larger than 3, and also you got x larger than 4. Let's talk about these two, just as an example. Okay. So now you got x larger than 3, and also you got x larger than 4. Okay, if you think about it, okay, for these two. So larger than 3 is going to be 4, 5, 6, 7, 8, 9, and 10, etc. Okay? Before I draw the set for x larger than 4, do you think it's going to be a smaller one or is a larger one? Smaller one. Would that be a complete subset? Yeah. It would be, right? Good. Okay. So now you can think about the way you can draw this is by saying it's just going to be something like that. It's like a subset over here, right? X larger than 4. Okay? Smaller one. Just smaller. You can think about for x larger than 3, it's simply going to allow one value that's not allowed for x larger than 4. Okay? So now, let's talk about weak versus strong. Okay? First of all, we know that x larger than 3 over here allows more values. Okay? In particular, the value of 4. Okay? And now, x larger than 4, we say that this is stronger. Okay? It's a stronger predicate. You know, always when we talk about stronger versus weaker, it's relative, right? So stronger because it does not allow 4. And how do we specify this in terms of a logical operator? Well, any idea? Conjunction, disjunction, or implication. So now we would say the stronger one, x larger than 4, implies x larger than 3. Okay? If you somehow can prove this, so that means the antecedent is stronger than the consequence. Okay? That's something just as a review quickly. That's something you will have to use quite often for this particular topic. Okay? So antecedents over here being stronger. Antecedents. And that's the consequence that's being weaker. Okay, especially I want you to make sure you really understand what does it really mean. When I say a predicate is actually weaker, because we're going to use that to talk about something called the weakest precondition. Okay, it's going to be the theme for the whole lecture. We'll get there today. Okay, but make sure you understand the notion between weak versus strong. Okay, the weaker a predicate is, the more values it can allow. Okay. Okay, so now you'll be stronger if you can you actually allow fewer values, the opposite way. Okay, and then implication. So now a very quick check by you. What would be the weakest assertion? True, very good. Okay, what would be the strongest one? False, very good, very good. Okay, quick check. Okay, so now let's talk about design by contract. So whenever you talk about, well, because precondition and postcondition and class invariant, they're simply specified using Boolean predicate, right? Boolean expression. So I can say a precondition is weaker than another precondition, right? That's something we talk about in subcontracting. That's also something we'll talk about as well. Okay, so for example, if you say invariant is somehow weaker, that means you're being more tolerant on the object states. For example, if I say the balance larger than 0 is definitely weaker than balance larger than 100. Because now, for example, if balance simply 99, it would be allowed by the first one, which is weaker, but it will be disallowed by the second one, which is stronger, right? Okay, that's one example. And also we talk about weaker precondition, right? Remember, whenever you got a subclass, yeah, you want to redeclare the precondition, you should require less. In that way, that should be weaker, right? Design-wise. And also, you may have also postcondition, it might be either weaker or stronger, right? So always we talk about these kind of notions. Okay, the first slide, nothing new. I just want to make sure you're okay with this. Any question about this? Okay, so we'll talk about weaker versus stronger all the time, okay? Just make sure you're okay with that. And then I will go a little bit further here. Okay, let's have some discussion here. I want you to stare at this particular program here. Very easy, okay? Let's say we have this particular design. It compiles, but we don't want to execute it. Before we execute it, we want to make sure it makes sense. Does it make sense to you? Anything that you don't think is appropriate over here. You want to really consider implementation together with contracts altogether. And one moment. Yeah, I'll give you a little bit more time. You really want to think about it, right? First of all, it compiles. Okay, compilation is not an issue. At the runtime, I would say it might be you're lucky. Maybe the test value that you choose is such that you don't really run into any violation, but you might. So that's why we want to do some thorough theoretical analysis over here. Okay, Chelsea, anything to say?
This is only lets one value.
Sorry, say it again.
This is only letting one value because we find that.
What do you mean only letting one value? Over here we say precondition here, I is larger than 3.
Yeah, so and when it's done, I have to sorry, go on.
Okay, basically, okay, let me read it to you and then I'll take your feedback, right? We're saying that in order to call this particular increment by 9 command, I value must be strictly larger than 3, which means 4 is okay, 5 is okay, but 3 is not okay, okay? And then if the precondition is passed, we're going to increment I by 9. Upon termination, of course, it's guaranteed to terminate because it doesn't have a loop. We want to make sure I is strictly larger than 13.
It will, if I is 4.
Yeah, seems like I is 4, right? Why is this wrong? Oh, first of all, let's agree. First of all, let's agree one thing, okay? When I is equal to 4, okay? And then 4 plus 9 is going to be 13. And then 13 larger than 13 will give you false. That means post-condition violation. So now there's something wrong. Where? The precondition. Why is that wrong?
Should be I is greater than 4 if we want to satisfy.
Yeah, basically somehow the precondition allows certain value that would have caused post-condition violation. Yeah, to put it more in a more general sense. Okay? So over here, we can conclude that over here, maybe too weak. So now try to really appreciate what I'm trying to say over here. When I say the precondition is too weak, so that means it's weaker than necessary, meaning that it allows certain value that should not be allowed. Okay, too weak over here. For example, it allows I equals 4, which will cause post-condition violation. That's not good because the precondition is supposed to filter out all the invalid input value for you, such that when you try to execute the implementation of your routine, you should really satisfy the post-condition, right? Question here.
Were we just talking about the precondition is 2 weeks? Because at the same time, the post-condition is...
Oh, that's good. Yeah, the post-condition might be too strong as well, right? Let's say, let's make this following assumption. Let's say we fix the post-condition. And also we fix the implementation, right?
post condition that
Yeah.
implicitly making
Yeah, I think you guys are making a very valid point. If I didn't tell you anything, of course, I will simply give you this fragment of code. I didn't say anything should be fixed. In that case, you may argue either way. You might say the precondition might be too weak, or you might say the postcondition might be too strong. In which case, maybe you should say that should be larger than maybe 12, for example, right? Rather than 13, right? Should make it weaker. So it depends on the context, I'm saying. Maybe I should have said, let's assume we cannot change the implementation and we cannot change the postcondition. In that case, the precondition is simply too weak. Okay? Okay, let's have a look at this very similar one. Similar. Again, let me make the assumption. Postcondition cannot be changed, cannot, negative, and the implementation cannot be changed either. Is there anything wrong with the precondition? Well, let me put it this way. Let me ask this following question. Can any can any input value that is allowed by the precondition over here, right? Larger than 5. Cause a postcondition violation. Very good. Let's answer that question first. I think that's the most important question to answer. If there's any allowable value by the precondition that can cause a postcondition violation, that means it's not good. You definitely got some flaw on your design. In this particular case, first of all, we know no, right? The smallest value that can be allowed would be 6, 7, and 8. So it's guaranteed it's going to be definitely greater than 13 for sure. So now I would say whether this particular precondition is desirable or not depends. There's no logical flaw over there for sure. However, whether that should be the one you need is another story. Okay? For example, what I mean by this is, let's look at this one a little bit more carefully. Let me put it this way. I larger than 5, right? Alternatively, can I say I larger than 4?
Yes.
Would that be okay? Well, if I ask the same question over here, it will also be no for I larger than 4, right? So that means either I can choose I larger than 4 or I can choose I larger than 5. And which one is weaker? I larger than 4 is weaker, right? Okay. I larger than 5 is actually implies I larger than 4. Okay? So now both are okay. But which one to choose when both are okay is up to you as a designer. That's my point. Okay? But now the green question I'm trying to say over here, that's really critical, right? That's how you judge whether the precondition is appropriate or not. When you got two options of the precondition that are both fine, it's up to you. Okay? Guys, any question here? Yes. Ah, good. You already talked about weakest precondition. Okay. I will get to the little bit more intuitive notion a little bit later. Basically, later on, let's say the implementation is fixed and the postcondition is also fixed. Somehow we have a mechanical way to calculate systematically what should be the weakest precondition you can have for your implementation to be correct. Anything that's stronger than the weakest precondition is fine. But anything that's weaker than the weakest precondition is not fine. So that means you will allow certain value that should not be allowed, okay, intuitively. Okay, but we'll get there. So that's why the notion about being weaker or stronger is so important, right? That's something we want to dig deeper. But nothing has been formal just yet. We're just trying to give you some example. Okay, so now we talk about these two examples over here. Okay, so exactly what I said. Okay, you can just refer to the slides. Let's give you a little bit of notion about software correctness. Again, let me give you a conclusion right away. By the end of the lecture, you might ask yourself, given what we have learned about the proof techniques for this lecture, do I have to prove every line of code for my projects or even the lab? The answer is no. In practice, people don't do it that way. You only try to focus on some critical feature or critical command that you believe you cannot necessarily test thoroughly. That might be the part you want to test on paper using the approach that we talked about in the lecture. Basically, you want to really combine testing and also proof together. That might be the best practice for you. Okay? You don't have to prove every line of your Java code or Eiffel code. You don't have to. It's simply not practical. Okay, we'll talk about correctness over here. Correctness is simply relative notion, which means given some particular specification, you can now talk about whether my implementation will satisfy the precondition, postcondition, and class invariant. It's relative. Okay, it's not absolute. Okay, so now this is something we have to play with for the rest of the lecture. Okay, let me introduce it to you now. It's something called the Hoare triple. Okay. Oh, by the way, do you know this person here? Just for your reference. Okay, you should know. Have you heard about a researcher by the name of Tony Hoare? Oh yeah, that's good. That's good. You're good. Okay. So Tony Hoare, actually, you already know about his work. He was the inventor of quicksort. I'm pretty sure you learned about it, right? He's a very well-known software engineer. Okay. He invented quicksort, and also he invented Hoare triple that we talk about today. Okay. So you did learn about his work before, quicksort. Okay. And he's a British, for your information. And he studied classics for his undergrad, not computer science. All right, let's see over here. Okay, so we're going to talk about Hoare triple here. Let me explain to you what exactly that means, and then we'll have some intuition. Okay, let me see if there's any slide I can go over. Okay, I'll go over these a little bit later. Okay, let me show you some diagram right away. Okay. Okay, I would say for now, let's try to look at everything together. You know what? Before this one, let me start a little bit more gently. This is how we can do it. Let me also give you some example right away. Let me copy this guy here, and then I'll start a new page. Okay? No, you don't have to. Hoare triple. Okay, basically given any program with the implementation and precondition and postcondition, and assuming that class invariant is just a postcondition for every feature, right? So we don't have to put invariant in the context. Okay. So now for every one of them, okay. So now this is what you can do. Here's the syntax. Okay. You're going to have curly brackets over here, and put something over here, and then you got curly brackets over here. Okay. First of all, that's the syntax. Okay. That's why it's called triple. You got three components over there. Okay? The first component over there is going to be the precondition. In our case, I larger than 3. Okay? It's part of the contracts. And the third component over there is the postcondition. Okay? This guy here. So that is the postcondition. In this case, that's I larger than 13. So now, as you can see, in the Hoare triple, the first and third components are both predicates, Boolean expressions. Okay? Precondition, postcondition, very easy to see. What about the middle part? The middle part, somehow, you're doing something like that for your projects because you are given some program structure, right? Like a grammar. You can think about it's more like what you're doing for the project. Part of it should be fit in the middle, like a grammar. Right, like a program like a program. So now what I will put over here is it's going to be just some program implementation. Like fragment of code. Well, in this case, it's going to be I is assigned to I plus 9. Let's get the syntax right first. Okay? You have to enclose the precondition and postcondition both being predicates into a pair of curly brackets, number 1. Okay? Number 2, whatever you put in the middle should be like a fragment of code. Okay? Of course, the approach we're trying to show you is very general. It doesn't have to be Eiffel programs. As long as you support assignments, if conditionals, and loops, you can do all the analysis, even in your Java code or Python code even. Okay? Okay, that's about the syntax. Okay? And then the next step is to understand exactly what a Hoare triple really means. Okay. Just mention again that the whole thing is called Hoare triple. What about the whole thing? Let me just get to the point by saying that the whole thing over here, if you think about all these together, this is a Boolean expression. The whole thing. Which means having the precondition, postcondition, and the implementation done, all the three components, the result is going to be a Boolean expression, either true or false. When would it be true, and when would it be false? Okay, I'll write it down. Okay, although just in the slide, but I think it might be nice mentioning that quickly. So now, starting, let me make it a bit thinner. Starting in a state that satisfies the precondition. Okay, over here, that's a precondition. If we execute the implementation, which is over here, if we execute it, then it will two things. Number one, it will terminate. Number two, upon termination, it's going to establish the postcondition. That's pretty much how you have understood every Eiffel feature so far, right? Given that the precondition is satisfied, we can execute the body of the implementation, and then it's guaranteed somehow the postcondition will be established. What if it's not established? Well, postcondition violation. In the case of Hoare triple, you're going to get false. Okay? It will, number one, terminates, and number two, establish the postcondition. When I say establish, it's simply a fancy word. It just means satisfy. Okay? It will just satisfy the postcondition. And if this whole statement is the case, then the Hoare triple will give you true. Otherwise, it will give you false. Let me give you examples where it will give you true and example where it will give you false. Okay? Let's do that. It's on the slides, but I'll rather show it here, so it's more connecting to what you have seen so far. Okay? By the way, any question about this so far before I give you some example? Okay? Basically, what I require you to do, just for today, we only introduce to a Hoare triple. By hopefully Thursday at least, given the Eiffel program over here, you know, number one, how to convert that into Hoare triple syntactically. Number two, understand what it means informally. We're going to do more formal things maybe next week. I will see. Okay, let me give you two examples. Number one, I will copy this guy over here. Okay, remember that's the very first example we talked about, which is inappropriate, right? Because the precondition is too weak. Okay, so now the corresponding Hoare triple looks like this. I larger than 3, I is assigned to I plus 9, and also I larger than 13. Put it more simply, okay? It would be true if the Hoare triple would be true if the program is correct. It will be false if the program is not correct. According to how we discussed, this should be false because somehow I larger than 3 is too weak. For example, when I is equal to 4, it's not going to establish I larger than 13 after incrementing by 9. Okay? So now, I haven't talked about any proof just yet. I want to give you intuition only. Okay? So now you can think about this whole thing over here is false. Because I equals 4, I equals 4 will be allowed by precondition. Okay, let's see another one. Okay, rather than copy and paste another page, can we just assume that for another alternative version, can we say rather than I larger than 3, okay, I'm going to say I larger than 5. Okay, just another version. Okay, I'm going to write in different color. If I use do that, how would that look like? I larger than 5. I is assigned to I plus 9, and also I larger than 13, right? You see, that's another Hoare triple, right? So when you have different alternatives for your design, you can try to write different Hoare triples and try to see if you can prove it eventually. Okay? So now this guy here, we also talk about it. You'll be okay, right? Even though it might be a little bit too strong, the precondition, but that's okay, right? So now for this guy here, it would be true because all values allowed by I larger than 5, which is the precondition, will establish I larger than 13, okay, the postcondition, after executing the implementation. I is assigned to I plus 9. I say we're okay so far? Everything's clear? Yes. And 13 larger than 13 is apparently false. So you will get, that's why it's false, because somehow there's at least one value that's allowed by your precondition that is going to be used in the implementation, but the final outcome will be you got a post-condition violation. So that's not appropriate.
And for the I greater than 5, because 5 plus 9 is 14, 14 greater than 13 is...
Oh no, if you think about I larger than 5, the smallest value you can use will be 6, not 5, right?
6.
Yeah, 6 plus 9 will be 15. That's already larger than 13, right? Yeah. Of course, you should be okay by saying, if I give you just one more version, okay, one more. Let me use maybe purple over here. Let me say rather than 5, let me also use maybe 4, right, over here. If I got I larger than 4 over here, I is assigned to I plus 9, and then I larger than 13, okay? Would this be true or false? True, also true, okay? And as we'll see later, for this particular example, I larger than 4 turns out to be the weakest precondition in order for this particular implementation to establish I larger than 13. Anything that's weaker than I larger than 4, for example, I larger than 3, which is weaker, is not going to be correct. Anything that's stronger will be okay. Okay? All right. Any question about this? Yeah, exactly. 14 larger than 13, yes. So that's fine. Yes. Yes. That's true. Correct.
What's a better design?
Oh, you mean I larger than 4 versus I larger than 5? I would say both are valid. First of all, both are correct. How about that? Both are correct. Which one should you choose? Depends on the requirements. How about that? Yeah. Yes. Oh yeah, again, so as I said before, this approach we are trying to show you is completely general. Apparently, I is assigned to I plus 9 is a very simple program, just one line. We'll, maybe either Thursday or next Tuesday, we're going to do a slightly more complicated program which involves a loop. But for your project, apparently, I'm pretty sure you use a much more complicated program. I would say, to what extent do you want to use this approach is completely up to you. Maybe you want to use only a part of it to say, only for this part, I want to make sure at the end of it, I can achieve something. That's something you can prove. You don't. You don't. It's not practical. You don't really try to prove formally your entire project. It's simply not feasible. Yeah, for those of you who might be interested in doing some master or PhD, in software verification, there's such a field. And there are different ways people actually try to verify program. One way is called model checking. The other one is called theorem proving. Right? There are different ways of doing things, but none of them really try to take a piece of working system and try to verify in its entirety. It's just not practical. You want to have some combination. But what's the end of the day, what's the take-home message? You want to do the most of the verification using testing. Testing is still really the way to go. Right? But formal verification also has its say as well. It's nice. Okay, so now let's go back to this guy here. Okay, that's exactly what I said. Okay, we just talk about Hoare triple here. Okay, so now again, let me emphasize again. The Hoare triple will be true if somehow you can prove somehow it is true. But how do we prove it? That's the question. Okay, we're going to show you exactly how you can prove it. Okay, Hoare logic. Okay, it's so-called the correctness predicate for your program. Okay, so you got a precondition Q and postcondition R. Okay, and also your implementation S over here. And then, okay, that's exactly what I said. You want to make sure starting in the states where you satisfy the precondition Q. If you try to execute the implementation program S over here, number one, it terminates. Okay, number two, it actually terminates in a state that's going to satisfy the postcondition R. Okay, so these are the two things, as I mentioned. Okay, now we're going to have a separation of concern, basically. Okay, we're going to talk about proof for termination versus proof for correctness, assuming termination. Okay, we're going to have two things. Okay, but I would say usually, if your program doesn't involve any loops, termination should be a no-brainer. It should always terminate. It's really the loop that gives you the trouble about termination. Okay, but we're going to talk about it. For those of you who are studying about 3101, have you heard about anything called loop variant? Looping variants? We're going to see that. However, I think this course is nice to give you a slightly different insight to looping variant because you can see how it is executed at runtime, which is quite different from what you did in 3101. So I think a complement, right, will help you a little bit. Yes?
So everything that all the architectures and the slides you studied, are they all always like, does or have it all been at runtime? Or have you covered
Sorry, say it again. I don't quite catch your question.
all the examples that we covered with respect to the tracing and stuff, say the double dispatching and stuff, is that all like shown in a runtime state as opposed to compile time state? Just to make this to be clear, like what all examples that you
Yeah, exactly. So far, the example, well, basically, so far for all the design patterns that we talk about, we study the static architecture, and then we also talk about how at the runtime it might work. And when we talk about runtime execution, you're going to talk about polymorphism, dynamic binding, etc., especially dynamic binding, and double dispatch. Okay, so now let me just let me spend a few more minutes just to talk about more. Okay, okay, termination, and when you talk about something about the correctness, but assuming termination, it's called partial correctness. It's not total. Partial in the sense that when you try to prove B over here, you don't worry about termination. You just assume it's going to terminate. Okay? Okay, whole thing is going to be called total correctness. Okay? Okay, the slide just for concept, right? So you can review that before Thursday. Okay, let's do a little bit more. Okay, so now we want to talk, okay, so we got this Hoare triple here, okay? Let's see a little bit more intuition here, okay? Let's discuss. Let's say we got Q being the precondition and R being the postcondition and S being the implementation. Let's talk about different combinations of Q and R. Let's talk about it, okay? Tell me how you feel before I show you the answer or some advice. What does this mean to you? If I give you this Hoare triple that somehow translated from some source program, what does it really mean to you? The final result would just be R. Why?
Because if the precondition is always true, then that result is just...
No, well, actually not necessarily. Okay, basically you're saying that any value I give, it will always pass the precondition, agree? Because precondition is simply true. There's nothing that can violate the precondition, number one. However, executing S, would it guarantee you will actually satisfy the R? Not necessarily. I'll give you one example. Let's say R is simply x larger than 0. R. S can just be x is assigned to -1. Okay? So now, let's go a little bit higher. So if you are given such program, what does it really mean? Is it good for the client or is it good for the supplier? Well, apparently for this particular program has no restriction on usage, right? Any input value is fine. Okay, so that's good for the clients. So that means if you are using this particular program or product, that's good. It's very user-friendly. Okay? How about this? Well, kind of the opposite, right? You will be very annoyed if that's what you can deliver at the end of the day. Your client would say, whatever I pass, doesn't matter valid or not, you will just be rejected. Okay, it's very useless. Okay. All right, and then what about here? How does that look to you? That means we got some ordinary precondition. Let's say we don't go for extreme cases for precondition, but now the postcondition is true. Is that a relief for the supplier or the clients? Supplier. So that means it doesn't matter what you do. If, for example, I want you to give me a sorting program, but you print to me hello world, right? It will still be fine because postcondition is simply true, right? So, well, that's risky for the client, but very good for the supplier, right? How about that? Would you hope your supervisor at work gives you such assignments? Well, what does that mean over here? It's impossible to really pass the postcondition, which means even if you got a big O of n sorting algorithm, it will still tell you that it's not good, even if, right? So you don't want to go extreme. Again, that's a lesson. Okay, okay, so now most challenging coding task, but it's just it's simply impossible. Okay, you don't want it. Finally, how about that? How about that? Wow, should both clients and supplier be happy? Huh? Well, you know, in some way they're both happy because they don't constrain, complete freedom. At the same time, it's useless, right? I tell you what, this is somehow how you will come into 3311 in the first place because you're not really used to contracts, right? It's like as if there's no precondition, no postcondition. You just kind of depend on the lock of runtime execution. Right? Remember what we said in the very beginning, maybe the second class or third class. We said pre and post conditions should be used to guide your developments. When you simply got both of them being true, it's as if you're not really using any design by contract, which means your design is not stable. No guarantee. Okay? Hopefully, once you graduate from this course, even though you don't really program this particular language anymore, you want to have that kind of mindset about pre and post condition. It's very useful design ideas. That's the hope. Okay? All right, it's not very useful. It's as if you didn't take any design by contract idea. Okay? Okay, so now, how do we prove about Hoare triple? Okay, I would say review up to here before Thursday. I'll stop here a little bit earlier, but I will start by going through the proof rules about Hoare triple on Thursday and then do examples. Okay, we still got 2 more classes to spare on this topic. Okay, I'll see you on Thursday.